Today we're speaking with Professor Gernot Frenking. Hello, I'm happy that you're here. The GDCH just honored you with the Erich-Hückel Award. What does it mean to you to receive this award?
I'm still deeply moved and greatly honored by this award because I know about the history of this award, the people who got it before me, and since I have now a 40 years career and I look back on this, and I look on all the other people who did great work, then I do say that it's something which moves me quite a bit. In particular, of course, that it carries the name of Erich-Hückel, because I personally was interested in him. He used to live in Marburg more than 30 years. I organized a seminar when he would have been 100 years old in 1996. I met his daughter, and I also was invited to visit the house where he has been. So many people talked about this personality. So it's particularly the name of Erich-Hückel which moves me. But in general, it's really a great award for me.
And can you say a bit about your research?
Yes, I think there is really a red line in my research, and these are the many aspects of the chemical bond. And I think my special attitude is that I am in my heart a chemist. Theoretical chemistry is a very broad field. You can make it from a theoretical point of view, from a mathematical point of view, from a physical point of view. I'm a chemist. I have to say that I'm a trained chemist myself. I got my high school degree only after I made an apprenticeship as a chemical assistant in a laboratory of Bayer. So from 1961 till 1964, I learned chemistry in a laboratory. And only after this, I received my high school degree. I stopped working in 1966 and got my high school degree in 1969, and then I studied chemistry. 8 years after, I started my apprentice as a chemical assistant at a big company, Bayer. And in my heart, I have always been a chemist. I learned all these techniques in a laboratory. I could it myself, and I liked it. The reason that I have chosen theoretical chemistry is not that that I did not like experimental work. I liked it a lot. It was curiosity. I was always interested, why? Why are those things happening as they are? And if you do this in chemistry, you go into the question on the chemical bond, because it is the chemical bond, it's not the atoms. You just have, in the periodic system, roughly 100 atoms, and 50 of them are not really important. It's the combination of the atoms, and it's the attraction of the atoms, and which is the chemical bond. And from a chemical point of view, the chemical bond is the basis of the complexity of the universe. You can take the living or the material world, whatever you have, it is the chemical bond which is the bonding. And this has, of course, a lot of facets, and you understand why it is so complex, why it is so difficult, why it is so wonderful at the same time. So it is really the chemical bond which I think has occupied all my scientific career. That's it. And you see, the history of the chemical bond is very, very interesting, because until 1927 there was no physical theory of it, no understanding. You could not explain it on physics. People were despaired about it. But you had already models for this. Models were very successful models, who survived this, who are still important nowadays. So you had a model before you have physical explanation. Normally you first have a physical explanation and then a model, but then it was the other way around. So there are a lot of peculiarities on the chemical bond. And if you take it very serious, then chemistry as one way of looking on the universe is just equally valid as it is in biology or philosophy or whatsoever. So lately I have been quite interested in understanding chemical bonding from a philosophical point of view, which brings me into a field. I'm not a trained philosopher, but which opens the door to yet another field. And I like it a lot.
And after you've studied and looked at so many chemical bonds, do you have a bond which is most surprising to you?
That's a good question. That's very good. Because it is just 1 year ago, or maybe 2 years ago, that we found a chemical bond which I had never thought that it would exist. And when we found it, it was so surprising that the paper which we got was immediately accepted in Science. And Science takes only, it's very, very different. They immediately accepted this. And this was when the so-called alkaline earth element, calcium, strontium and barium, form chemical bonds like transition metals. For me, calcium, strontium and barium from the point of view of chemical bonding, were the most boring atoms at all. And so if you would have asked me 5 years ago, look on the periodic system, which atoms have really boring chemical bonds, I would have said, look on the earth alkalines, and beryllium is something which is special, yes, also magnesium. But when you go to calcium, strontium, barium, that's boring. And it turned out that they are perhaps the most surprising and fascinating so far. We got a second paper in Science recently when calcium is even capable of breaking the strong bond in N2. So N2 activation can be done by calcium. That was done in cooperation with Sören Harder at Erlangen, who is now working on this experimentally. He found out about it. So at this moment, I have to say that the chemical bond of the heavier earth alkaline atoms are for me the most fascinating ones. But I'm not saying that there are not other bonds which still may come up. Nature has so many ways of getting interesting bonds. That's amazing. No, it will never stop.
So how do you find bonds which qualify for your research?
The thing is that I think a quality which I do have is the following. You see, you get tons of experimental publications every day. All of them, and of course I read the top journals. I read Angewandte Chemie, I read JACS, I read Chemical Sciences, all of them, and I go through them. And I think what my quality is that when I see new molecules, I immediately I try to get what kind of bonds are there, and in which class of bonds do they fill. And I have a good feeling that I suddenly see, oh, this is something peculiar. This is something unusual. So I have the quality to find out chemical bonds which do not fall into the category of known concepts. You know, the bonds have certain categories, and it's like you have a field of flowers, and there are already 100 flowers or 1,000 flowers, and people report about yet another one, and suddenly I see a flower that doesn't belong on any of this field, is perhaps new. And sometimes it happened that I contacted an experimentalist and said, what you have found is really something which doesn't belong to the usual category. And sometimes people made it, and have not really realized what they have in their hand. They have this compound, it's red, and I do have a few examples in the history where I approach experimentalists and say, come on, there's something totally new. And not always it turned out positively, but sometimes it did. And then it was the starting of a new, it's like opening a door to a totally new field. It also meant the other way around, that experimentalists approached me. After some time I got a reputation for being a specialist on chemical bonding and saying, look, we got something what we cannot really explain, could you have a look on it? And then I looked on it, and sometimes I found out, sometimes it's an experimental error. People make errors everywhere. Sometimes I found out, well, it's somewhat unusual, but it falls into the category. But sometimes I did find, oh yes, this is something which is totally new. This is unheard of. And then it was like the door is open to yet another room. And that is wonderful. Being the first one in the room, you immediately you can see how large is the room, what kind of flowers can be there in, and this calcium, for example, this is calcium oxycarbonate. This is one was wonderful. We immediately stumped into the room and said, "Can you do it with CO? Can you do it with N2? Can you do it with benzene? Can you do it this?" We are still not at the end. We are still working on this. But we immediately opened the room and filled new flowers in it, and found new examples. That's wonderful. Being the first in a new field is great. And I do this for a couple of years, and when there is enough flowers, then it's fine. Then I'm looking again for, is there something?
Will there ever be enough flowers?
Yes.
Yeah, you just said you're still active in research.
Yes.
And you're having a visiting research professor in China and one in Spain. Can you say a bit how this works? And
yes, particularly the one in Spain is wonderful. When I retired in 2014, I had a contact with a colleague at the university in San Sebastian, in the Basque country. And the Basque country is a very special place in Spain, not so well known, but the people over there have a special regulation that they can keep their taxes. So in Spain, all the different accounts must give their money to Madrid, and Madrid distributes it. The Basque country has a special regulation. They have to give a certain percentage, but they keep the rest for themselves. And the Basque country puts a lot of money into research. And they approached me when they heard about it and said, look, we can offer you a visiting research professorship for a period of 7 years. Every year you can come up to 6 months. You choose the length, the time, and what you are doing yourself. That's all. So when I come there, I get a payment, and I can do just do my research. And I did it for. Do
you have students there, or?
No, well, I can. There are students. So if I have a project, I can approach them and say, look, I work on this project, would you be interested in doing this? But I don't have to. They gave me total freedom. They give absolutely freedom. I can continue working with other corporations. Since my retirement, I still used to have a postdoc in Marburg, but I have corporations all over the world, which is former co-workers of mine. So I never had problems of finding people working with me. But when I came there, then I really had the total freedom just doing research, and that was great. And I did it for 5 years. This year was the 6th year. I couldn't go because of the virus, but next year I will definitely go for the last year. So this was great. The other research professorship is in the University of the Nanjing Tech University in China. A former co-worker of mine, a postdoc, Lili Zhao, was with me for 2 years as a Humboldt Fellow, and she returned to China also in 2014. She became a professor, but then she asked me, would you like to continue working with me and helping me a little bit? And I said yes, and then she wrote me, well, if you do this, we could offer you also a visiting professorship. And I said, I cannot come very often. I have this in Spain. And she said, well, you don't have to come. So I don't have to be, but I came to Nanjing about twice a year for just a week, just to see what's going on. And the advantage is, in Spain, they give me the freedom, and they give me also a salary, but that's it. In China, they gave a lot of equipment. So the equipment which was given there to my former co-worker, Lili Zhao, is also to me, and also the positions were given to me. So I could hire postdocs who were willing to go to work in China. And I have a lot of computational power there. They had a lot of money, so we could buy a very large PC cluster. So whenever I have a project and I want to have someone working and I don't have it somewhere else, I go there. So this is in a way my external group, which has a lot of computational power, and that is a lot. So whenever I find a project which I want to work on, I send it to Lili Zhao and to her students, and they work on it. And I don't have to be there. As I said, in previous time I went once or twice a year for a week. That's all. But I rather spend my time in Spain.
You once said in an interview that science is first and foremost a cultural achievement without material value creation. So is this emphasis on basic research over applications of research? Is that realistic, especially from you've been a DFG reviewer for a long time.
I'm very grateful that you asked me for this. I have a transparent picture in my lecture. Basic science, fundamental science, is like planting the roots, but you do not know what fruits come out of it. Some fruits may come out of it. You cannot have fruits without the roots. And basic science is permanently planting roots without really knowing. So when we calculate new molecules, when we calculate new things, we help experimentalists to make these compounds. But nobody knows what the property of these compounds are. And the industry, fortunately the industry in Germany, the chemical industry knows about it. They also do support to a certain degree fundamental science, because they know, well, there might be some compounds which have properties which are very important and helpful for us. So funding fundamental science is of fundamental relevance for the application. You cannot have without the other. And here I have to give really credit to the German Science Foundation, to the DFG. They know about it, and they are very, very strong in supporting basic science. So I do think that in Germany we have a comparatively good standing compared to other countries, and I particularly see the United States and I also see Great Britain, where they immediately are under pressure. What comes out of it? And you do not know it. Fortunately, in Germany, and thanks to the German Science Foundation, the DFG, the Deutsche Forschungsgemeinschaft, they do support good science, quality science, independent of what is it good for. What is it good for? You only know afterwards what it is good for. Don't forget, science is just is trying to address the curiosity of mankind, and curiosity is a typical characteristic of man. Otherwise, we would be economical animals. We do need economy, clearly, but from a cultural point of view, the satisfaction of the curiosity is of uttermost importance for mankind. That's something which I'm sure. And it does not oppose application, absolutely not.
And is some of your research used in a company somewhere?
Not to my knowledge, not to my knowledge. But you know, this kind of research enhances the knowledge in general, and you do not know what it's like a building which has 20 floors, and 20 floors does not know that it is built on the second floor. So when we, for example, the nitrogen activation with calcium, which we found due to this transition metal chemistry business, it may turn out to be important for nitrogen activation. If this would be, then this would be true. That it's a holy grail of one of the holy grails of chemistry in general. So I do not know it immediately, and because I'm too far away from the immediate application, too far. But I know that students who are trained with me, they do know computational chemistry. They might go then into a company and then they take this knowledge about calculating compounds, and then they go there directly into application, particularly drug design, which is an important area. And some of my former students went afterwards into drug design. And then the question of application answered itself.
Yeah, that's fine. Okay, so thank you very much for the interview.
You're very welcome. Thank you. Thank you.